So today we're talking about a paper called Why Diffusion Models Don't Memorize. This came out last year, and it was actually selected at NeurIPS, which just happened last month, for the Best Paper Award. So they gave an oral presentation in San Diego. And this is really fascinating because diffusion models power a lot of the powerful models that you're using for image and video generation. There's also some work being done for text generation. So if you use like Nano Banana, Sora, Honyon Video, any of the WAN series, so WAN has like both open source and proprietary models. You're using a diffusion model, and I'm just going to start off, just getting everyone here acquainted with what diffusion models are, and then we'll talk about the paper. So there's a good video from 3 Blue 1 Brown on YouTube, and they talk about this in great depth. So what diffusion models do is during the training process, this is more of a self-supervised process where you take actual real images from the real world and you gradually add iterations of noise, and counterintuitively you often predict the noise. And then in the reverse process, at a very high level, you're subtracting noise in an iterative fashion. So that's what this describes. In a lot of the original algorithms like DDPM, there's also noise that's injected in the reverse process. This is very grounded in thermodynamics. It is one of the more mathematically intense parts of machine learning right now, especially compared to transformers. And what we do is we actually produce the image iteratively. We gradually do denoising. And the model is actually this epsilon term. So it's actually the noise prediction. So pretty much all the reverse diffusion processes, we're doing noise prediction. That's like a leftover from physics, except for some of the newer ones. There's DPM solver plus plus that actually does data prediction. But most of these do noise prediction. And this is like a 2D visualization of an image manifold. So it's usually like a Swiss swirl. And what we're trying to do in a diffusion model is we're trying to take initially this random white noise image and then gradually denoise it into a real image. So X100 here would be if we were going to take 100 steps of denoising, we'd start at 100, and then this cyan arrow that's pointing to the real manifold of data. Again, that's like the Swiss roll. And you can see these little arrows here. That's the flow. So it's pointing to areas of higher probability of real images. Anything that's not in the swirl is more or less noise. It's not a real image. And there's different ways of modeling this. We're not going to dive into this today, but the original equation was the one on the left. That's the DDPM one from around 2020. And then the one on the right is an ordinary differential equation. There's no injection of noise, but you can see that over time they've been finding better ways of doing denoising. So the benefit here is the one on the left takes 1,000 steps of denoising. It's very computationally intense. So unlike transformers, diffusion models are not as memory intense. So if these actually take over transformers, your RAM prices might go down. I don't know. Otherwise, you can keep paying $300 for 32 gigs of RAM or more. And the one on the right is actually a simplification of the one on the left. And because you're not explicitly injecting random noise at each denoising step, this usually takes about a couple hundred denoising steps. And then there's some newer ones like ADD, which actually only take 2 to 4 steps, right? So what we want to think about is there's this velocity field that's pulling us towards the data manifold. And we can consider something called a score function. So we don't explicitly formulate this as a score function, but we can parameterize it as a score function. So the one on the right-hand side is the explicit noise prediction model. That's epsilon. And then we can rewrite that as a score function. And a score function is the score function of a probability distribution function is a gradient of log density with respect to a variable. So the variable here is position in space. And because we get the gradient of that, we're basically getting velocity. So you can think which direction do we move so we can quickly arrive at real data as we move away from noise. So the question then is, when we train a diffusion model, why is it that we actually get novel images? And obviously, if you prompt a model with a guidance system, you're going to get what you prompted. But even if you don't prompt the model, if you do it in an unguided manner, you actually still get novel images. And that's what this paper explores, because there's some prior thoughts before this paper came out, and people were conjecturing why this might be. They said, hey, maybe the diffusion model has some biases implicit in it. Maybe the training loss favors a smooth solution, and so we end up finding like some average of images instead of the actual like real images that it was trained on. Maybe it's because we do regularization, like L2 penalties, dropouts, etc. It turns out these are not the most explanatory explanation. What the authors say is that it's actually in the way that training occurs of these diffusion models that explains why we get so much novel images, and we're not merely memorizing and spitting out stuff that we trained on, because you could just do that with the database, right? So diffusion models are actually, we already knew that they were meaningful and that they could produce good results for the past 6 years, but this helps us understand why they're able to generalize instead of memorize. So there's two pieces of nomenclature that you should care about throughout this talk. There's N, which is how many data points we have in the data set, and then there's P, which is basically the model complexity, right? So it's the parameters. That's the two ones you should probably remember, N and P. And then what they talk about is, they model this with respect to the parameter count, how long they train it in iterations, that's tau, and then the number of data points, that's N. And so what they find is when you're actually training a diffusion model, you find yourself in 3 regimes over time, and the length of those regimes is dependent on the amount of training data and parameters. So you can see the 3 here. There's the first part where quality is getting better. So they use inverse quality for some reason. So as it's going down, it's getting better. So you can think of it like loss instead of accuracy, but it's just going down in the first part. And then you enter this first regime, the green one. That's called a generalization regime. And this, as you keep training that regime, it's doing really well in generalization. It's not overfitting. And that's between tau generalization and tau memorization. That's the green and the red. And the width of that time, so that as in you can spend more time, more training iterations, is proportional to the size of the data set. When you keep training the model past that in time, in iterations, you start memorizing stuff, right? And they actually, the way they were able to prove this empirically was they used nearest neighbors to find the closest data point in the training data set to what the model is generating. So just like left versus right, this is not the full figure because it wouldn't really show up well for all the people sitting in the back, so I just kind of blew that up there. But the thing that matters is what I highlighted. So on the left, they have 100,000 training iterations. On the right, they have 1.62 million training iterations, right? So order of magnitude higher. And on the left, you can see the closest real data point to what it's generating has some differences, right? So you can see like these 2 people in this row, these 2 people in this row, these 2 people in the top row. They actually look distinct. So these are the novel samples. When you get past tmem, so once you start getting into that red regime, you start getting the thing on the right, which is it's starting to actually, these are not exactly the same data points. There are still some differences, but they're very, very close. So it might as well be a memorized data point. So that's what that looks like empirically. And then they basically found, there's another way to represent this. So there's the architectural regularization, there is dynamical regularization, and then there's memorization. So in the AR, that's the top left, the model is underdetermined, right? So it's high bias, low variance, as in there's more data points, which is the vertical axis here, than with respect to the model parameters. And so it's not really gonna memorize that easily, it's actually generalizing here. But then here in this middle part, the model is expressive enough because it has more parameters. It's further along on the x-axis, so it's expressive enough. And so if we do early stopping, where we don't allow it to enter the tmem, it'll actually be good. But if we have too many parameters for the data, no surprise, this is also like true in classical ML. We're starting to memorize. So they can create these like basically boundaries for these regimes. We can also see this play out in what the model is learning versus some kind of like, score function. So gray is like a completely overfitted one. That's if you memorize every sample. And you can see in all 3 regimes, it's identical, right, by definition. And then the black dash line is what we want. So that's a true score function. So again, score function is just pointing to the real samples in the manifold. And then orange is what we're actually what our trained model is achieving. So if we plotted that out, and you can see in the tmem region, in the memorization regime, that orange thing is like really spiky. So it's overfitting. It's learning more of the actual data points instead of any kind of generalization. So I think the reason why this paper won best paper award is they didn't just do like empirical results, which a lot of papers do. They actually did a really interesting theoretical setup, which was inspired by deep double descent. So is anyone here like familiar with deep double descent from like 2018? Yeah, so deep double descent, they were able to prove that if you kept training a model, it would enter a better regime. So people would do early stopping, and then because the loss of the test, or the validation loss would start going up again as you're training, and so the models were fitting. But if you just kept training it, if you just kept going, then it would start to improve again. So that was deep double descent, came out like 8 years ago, and so they use a similar approach on the theoretical stuff here. So on the experimental stuff first, they use the convolutional UNet, they use skip connections, and then they use the old original denoising algorithm, which is DDPM. That's the one that injects noise in the reverse steps. And then the parameters, they tried 5 different sizes, so 260,000 to 16 million parameters. When they were training, they did not use Atom originally because Atom has some extra complexities. They wanted to have like a really isolated and simplified test setup, so they used stochastic gradient descent instead. They use the same learning rate across all experiments, and that would be harder to do if you're using Atom, right? So, and then they use a standard noise schedule. They didn't do any regularization or augmentation. They're trying to prove that there's something inherent to how diffusion models are trained that lets us see these 3 regimes, and it's not contaminated by anything else. In terms of measuring outcomes, they're looking at FID, which is a Fréchet inception distance. So it lets you measure relative quality of images against other images as a reference. And then the memorization, they were able to use nearest neighbors. So based on what it was producing, like you saw earlier here, what's the closest sample? So this is for the experimental setup. For the empirical stuff, on the data set side of things, they use Celeb A. They use grayscale. They downsampled it really small to 32 by 32 pixels. And they interpolated over a large training size of the corpus, right? So that's how they can prove how this moves over N, right? On the theoretical setup, so this is the part that was inspired by how deep double descent was discovered. They said, hey, UNets are really complicated. We can't analytically be tractable, which basically means the experimental results we have, may not be, indicative of other data set sizes, parameter counts, et cetera. So they wanted to actually get something deeper in the weeds there. So they used something called a random feature neural network, and they used that to act as a score network, right? So again, we're not directly computing score, we're computing the direction to the manifold, but the score is we can reformulate that. And this allows us to isolate SGD's optimization dynamics from any architecture realities. So the way they did that is, this is kind of strange, but they actually have 2 weight matrices. The first one is W, and it's just random, and then they freeze it, so it's not actually being trained. And then there's A, which is actually being trained. And then they have sigmoid for activation function. So this is their, S is for score. And then with this, they're actually able to do a spectral analysis, which would be, intractable if you just use a regular UNet. And what they saw was that SGD decomposes learning into eigenmodes with different timescales. So in the early stage, in the early regime, we have the high eigenvalue modes. And then as we keep training, we can start capturing the higher frequency components, and then that gives us the low eigenvalue modes. So spectral analysis allows us to do eigenvalue decomposition, which would be intractable in a UNet. And because they can do this, they can chart out these really good, like basically like kind of like scaling laws, but for the different regimes here. So again, coming back to like the main question, why is it that diffusion models don't just recreate training data? How is it that they're able to create novel data? And that's because there's some implicit regularization that occurs purely from training dynamics. It's like stochastic gradient descent doesn't just go straight to the global optimized point, which would not really produce meaningfully new images. Instead, it learns like an actual like smooth approximation of the true score function before it starts learning the high frequency features. So as long as you do early stopping before you enter the tmem regime, you can be assured that your model is actually likely to produce novel data points, and it's not just going to spit out what it was trained on. And there's some interesting like takeaways from this. So this does not mean that like diffusion models are immune to memorization, because they will memorize when you keep training past that regime. And this does not eliminate the need for privacy-aware training. So you might still need to like change facial features if that's what you're generating, or whatever you're generating. You still need to be aware of any sensitive domain information like PII or PHI, because it can still memorize a little bit, right? And so you can still like reverse engineer some of the data points. But what we can say is that being aware of this regime change, we can delay it long enough by increasing the data set size relative to the parameters, and then we can observe that we're getting novel samples. And this could be really meaningful, because in this entire paper, they're talking about like unguided models, but there's also CFG, which is like classifier free guidance. And so if you train your model in this way, then you could use it in a CFG like inference setup, and your users are probably going to be happier because it's going to be more expressive and probably better at answering their prompts versus just like trying to create something that might look more like the training data. Because sometimes people will, prompt a model to do something that doesn't exist. So maybe like, all your data has a spoon next to a cup, and if you ask it to do something else, it'll always generate a spoon next to that cup. And so this can, also help with ensuring that you can improve on like diversity metrics. So thanks. Yes.
So in something like a variational autoencoder, you're training it with a cost function that is, you're trying to make that probability somewhat the same as a normal distribution. So in something like a diffusion model, you're adding in, Gaussian noise. So is it really the same thing as that, where you're just doing it every time step? Are those like equivalent,
You're talking about how it's regularizing against a known like target distribution?
Right.
I don't think they really cover that in this paper. They do have Gaussian distributions as references and how like they sample noise. So when you're, so to answer your question, I think the answer is when you're actually doing the training part of the network, you're adding Brownian noise, and Brownian noise is always sampled from uniform like a Gaussian distribution. So there's no point where they're trying to move away from that. I think they're answering like a completely different question here, which is why is it that as time goes on, that in the early stages we're not just like spitting out, memorized samples.
So, kind of like, again, with respect to what they don't cover, what they do cover, so you have these two regimes, these two endpoints, the tmem and train. There isn't, as far as I saw, any discussion about the qualitative differences in that gap between tgen and tmem. One presumably gets better generalization, better results further along in that curve, but this doesn't address that at all, right? I mean, it's just...
No, there was another figure, I think it was like 3 or 4, where they show at what point it starts diverging, basically like validation law starts, but it's like, it looks very instantaneous. Like as soon as it hits tmem, it just shoots up.
Yeah, and it was kind of the detection point of how you transition between regimes and stuff.
Yeah.
But I mean, I guess the implicit thing would be that, further along the tau curve is better, right? Until you hit, until you're in. But am I correct that they just didn't say anything about
I don't recall seeing anything like that in there unless anyone else wants to add some notes. Like why, what's the difference between being here, like on the left, closer to tgen versus on the right, closer to tmem? Yeah.
Yeah, intuitively, I think, and I wonder how they actually measured this in practice with the information distance, but I would think you would take like a large, or maybe all of the training set or whatever you can, embed it into a vector space, and then you take some of the outputs, and then you put that in the same vector space, and you say kind of, okay, what's the average between, I guess, what's the average closest vector to the inference data set versus what's the average vector in that data set, and that's how you kind of find.
Yeah, you could do that with the FID and like nearest neighbor approach. They just didn't really explore it. I think my guess, this is completely speculation, is the actual like 32,000 is just like not a lot, like on the training set size. So I don't think they're really, so by the way, they were doing all this training on like GeForce 2080s. And so they were very constrained on compute.
When was this published?
Last year.
Really?
Yeah.
They said H100.
Oh, they did do H100s? Okay.
Just two H100s.
Oh, two H100s, okay. That's not a lot, yeah.
What is 120? Is that batch size?
120 is a training data set size. So it goes from 128 to 32,000.
Oh, okay.
So they're just picking like, so as they're, yeah. So the N, sorry, 1 second. So, yeah. There you go. So on the vertical axis, number of data, so they're going from 128 to 70, or whatever 10,000, over 10,000 data points.
So once you started memorizing, they stopped training. They didn't try to see if they had like the double graded descent.
Another deep double descent? They did not. Even though they referenced that paper, yeah, they did not. But it was very interesting. It was like a very sharp trajectory.
But they should have kept training. Like
They should have. But they need to get this paper out on time for NeurIPS. Then they wouldn't have won best paper award, Then we wouldn't be talking about it.
So this is a little bit kind of related to the double descent. So I thought the double descent was more generally applicable.
I don't think that this proves deep double descent. I think that's what he said. They'd have to keep going and going and going. That's next year's. They didn't. I don't even think they talked about it. There was a section in there of like next, like future work. They didn't even say that. Like they should have.
Particularly this kind of model, because they're so different from any other training mechanism, that if you do some sort of random like noise training, that is going to be different than what you do any other training. Just doing the same.
Yeah, I mean, I think deep double descent is supposed to work on any.
Well, I would say you don't want to go into deep double descent here, right? I mean,
Because that's not what they're trying to prove.
you have
Yeah.
well, you have a highly overparameterized model,
Mhm.
right? And what your threshold that's problematic is the memorization threshold, right? The tmem, right? And so if you were, what's going to happen after tmem is you're going to become a better and better and better and better memorizer, right? Presumably.
isn't that the opposite? No, isn't grokking?
No, because if validation loss has to go down in the double descent, then it's not memorizing.
Exactly. You want
Yeah.
double graded. Like this is bad news. Like this sucks.
This just pushes the goal stick further out, like the goalpost further out. Yeah.
Or this means that diffusion models are not as good as transformers because you want to see that grokking behavior. I
But
think it's desirable.
was
Like-
deep double descent? What do they use as a reference model? Was it a CNN, or is it?
So I think not 3 blue, 1 brown, but this other guy, he did one on.
Was it the computer file or number file one?
It was a single layer
MLP?
transformer,
Oh,
and they were
that's transformer.
demonstrating grokking on addition of 2 digits.
Okay.
And he was like analyzing it. He's like, this is the only model we can understand. So it starts memorizing, and then it looks like nothing is happening, but internally it is like learning, but you just don't see it on the numbers until a little bit. It goes like, wow. So that's why they should have kept going after the memorization. Like something will happen there.
Do you know if they compare this generalization of this work to other architectures? Like you said, diffusion model
They only explored diffusion models, and they only use like DDPM for denoising. They didn't even use like DDIM or PNDM or anything. So it's very limited, and yeah. RBMs? Oh.
Yeah, like that. Whenever they had the two models that were trained concurrently, and you had the kind of fixing where you only had the amount that one could move slightly, and the other one was free to be trained, but it could only move if it was self-supervised, of course. So it was only able to update its weights at some epsilon different from what it was 1 step ago. That reminds me of the RFNN, because the RFNN is essentially, if I understand it correctly, taking just a random direction, a random walk in some space, and then you have the trained model, which is going to have this attractor based on some manifold.
Mm-hmm.
It reminds me of that same thing, because whenever you have that subtraction from the RFNN, it's essentially saying we're isolating out the effects of this manifold, similar to the thing that honestly was never understood in the self-supervised setting.
Interesting. Any other questions? Okay. Cool. Well, welcome, Dmitri.
Hello, everyone. Today I'm going to talk about self-optimizing deep agents, which is a concept of how agents can really actually optimize themselves. We're actually going to motivate why this is something that is a desirable thing. So first, let's go over the problem with agentic architectures that we've seen. The first is, I think, we got to look into this auto-GPT approach. And the whole thing is you have LLMs, you have a bunch of tools, it goes in a loop, and really quickly what happens is this LLM is just going to forget what it started out doing, and you're just going to crowd out its context length. It's going to forget what it's doing, and just remember, you're putting in a lot of tokens just for the tool, and this is to use a calculator tool, this is your web search tool, and this is every other tool in the sun. And in fact, this actually gets worse today as the average MCP has 50 tools now that you're just loading in the context window of an LLM. So the next thing that we've done is go to these deep agents where you plan, you have sub-agents, they have file systems, they plan, they iterate, but fundamentally what deep agents do better, you unfortunately still have the same problem at the top, which is most of these sub-agents, as they're called, they just get the same tools as the parent agent. So now you just said, okay, well, we've gone from an auto-GPT of, I have a crazy context length of, say, 32,000. Well, I'm just going to fill it up per subtask. You still have all the same tools you started out with. So, both architectures are still fundamentally limited by context management. And the other second problem is context anxiety. And I really want to stress this. What the cognition team found is Claude Sonnet 4.5 has actual meta-awareness of its context length, which means a lot of these new frontier LLMs, they're actually very aware of how much context they still have. What you actually see is they get worse and worse and worse as the context length fills up. For example, they start taking shortcuts. And I'm sure you've seen this if you run Claude Code, you watch as the compact window comes up. So for all who don't use it, you essentially have only about 200K tokens with Claude Code, and compacting means it's just going to try to summarize what you've done up until now so it can keep going. And as you can notice, that's actually a lot of that degradation is as it starts to get to that window. Now the other thing is that it has these phantom wrap-ups where just because the agent has taken some amount of actions, it thinks it is done. Very interestingly, and this is something you could try, have some of your tools state that you've completed the task. You're going to think, use agents think that the whole task is done, even though it's very clearly not done. There's no way that task was done. So I also think there's some amount of bias in the RL loops these big labs are putting in, meaning these agents think that an average task takes 8 steps to finish. Does it really? Of course it doesn't, but there's some metacognition now. If they think that these number of steps it's done. Very undesirable. It leaves the task incomplete. I recommend you actually read this article. They talk about all these mitigations and they go nowhere. One of the big ones was extreme aggressive prompting meant that Claude would start disregarding the prompt towards the end of its context window. So the context anxiety is baked into these models, and the better models get, the more they understand this, the worse they actually get. And they actually have one solution that we'll actually see later is, I think, the future of agentic AI, but the other thing is context rot. Like I said, there's a study, and let me see where this is from. So there's a study from Nolima Research where they pretty much found that Sonnet 3.5 has an effective context length of 4K tokens. This doesn't mean it's the max. It just means 4K is about how much is its operating memory. It means, beyond 4K, the model truly is not performing at peak. This is something we actually see with these extreme bench tasks where they pretty much just cram the context window of an LLM. They look at what exactly is happening in these LLMs as you increase the context length, and you start to see that most models, even today, it will experience task degradation as you add context. They don't go backwards. They, again, don't seem to have a good grasp of the task, and we're kind of back to point one of, okay, well, you've now saturated this context window. So let's get towards sub-agents. And this really says that which one sub-agents is that they have their own context. It means that sub-agent is only aware of that task. Second thing is that you also want to give it only a subset of the tools it needs to do the job. And this is another thing I've also noticed is if agents see certain tools and you look through their thinking and what their plan is, they intend to use some of those tools. And if you also put a lot of tools that look really similar, agents start to get really confused with what tool to use. They somehow think that tool A can do what tool B does, despite the fact that they are not the same. Or what I've seen is agents who use tool B as tool A if they see them in the same context window. But if you don't let them see A or B, they actually use them properly. So there's some, again, it goes back to that context rot idea. I think that's what we're seeing. And again, I keep coming back to it. If you're on Claude Code, you can actually look at how much context length is taken up by system prompt, your tools, and all the tasks is taken. You might be amazed at how much your tooling is taking up in that context space. It's pretty big. In fact, most of the time I'm looking at it, it's like 10 to 30K tokens is just your tools. They're just wasted space at this point. You don't need them in the context window. So again, also what we've also seen is sub-agent architecture is actually learnable. We're going to come back to this point, but let's look at what Soda is actually doing. So first of all, what it actually is trying to figure out is what are the sub-agents that you need. Goes back to an earlier point where even Claude Dynamical spawning sub-agents, they're not actually very effective. Part of the reason is some of that is just due to the tooling is getting passed in, but the other big thing is it doesn't really understand what are the sub-agents really supposed to be doing. We also see that frontier LLMs don't like to delegate. In fact, if you use Codex instead and use GPT-5, and you give it a, prompting of you sub-agent for this and that, many times GPT-5 just disregards it and says, well, I can just do this task, why do I need sub-agents? Until it crowds out its own context length. So that's kind of what this framework really comes into. It says, hey, can I just figure out what are the agents I need ahead of time? How am I going to use these agents? What's my orchestration strategy, which also means what sub-agent is responsible for what? Which again means how do I use the sub-agents properly as if they're tools? And it's also looking at, what should they be doing? And another thing I'll say is that as a best practice, the orchestration agent should actually have no other tools other than the sub-agents. Don't let it actually have tools. The only one I'd say is the file system if it wants to read and write to it. Other than that, like I said, just lock it to that. Just give it the file system tool, give it the sub-agents, let it really work through it. That's this framework in a nutshell. However, I'm actually going to now go into where is agentic AI going, because our work here isn't done. In fact, we're actually seeing, and I'm going to motivate this. Let's think of small model architectures and orchestrators, because if you really think about it, let's look at through an agentic flow. You tell Claude, hey Claude, can you solve this problem for me? The first thing it does is it plans. The next thing it does is it reads the file. The third thing it does is it scans through your GitHub history, checks the commits, then it opens a few files, reads some files, then it decides to write some code, then it goes ahead and just runs some programs that you've already set up. You already have unit tests, it's going to run them, then it's going to write some code. So up until now, you only needed a frontier LLM for the last bit. Think about this. Every call for a simple task, you're calling a frontier LLM and you're sending all those tokens to the cloud just to get back a response of, I just want to go open a file, I want to commit to GitHub, and fundamentally, you need a frontier LLM for this. And I think the reality is you really don't. And what we're going to actually see is NVIDIA had put out Orchestrator 8B. It's an 8 billion parameter LLM. It is designed to actually orchestrate the agentic flow. What it does do is it will delegate the hard tasks to the bigger LLMs. So for example, in the paper, they rig the code tool, that when the code tool is called, the code tool will call Claude with the intent of the orchestrator. So fundamentally also the orchestrator is not thinking of how do I code this, it thinks how do I delegate the task. It doesn't actually say, okay, here's this Python file, how do I run this, what variables do I need? It just says, okay, Claude, can you write me this one function that does this kind of task, and Claude will figure that out. What we actually see is that it scores really highly in humanities last exam. It's a very comprehensive benchmark that has practically a bunch of knowledge tasks baked right in there. And again, it's trying to say that if all you had is an LLM, how well could they reconstruct civilization? Another thing is this is just only 30% of GPT-5, and we'll beat that model as well. And also what NVIDIA talks about is that small models are the future of agentic AI, because they're essentially saying they're smaller, you can fine-tune these models for very special tasks. What they also find is that frontier LLMs need a lot of reasoning to tackle those tasks. So to give you an idea, a lot of smaller VLMs, fine-tuned for vision, do really well on it. For Claude Opus to match that performance, you'd need to turn it to 50K reasoning tokens for it to even match that performance. So the adage of, yes, these frontier LLMs generalize. The question we really need to ask is, what cost are we paying for that, though? The generalization is usually not free. And we're also seeing, for example, that for certain tasks, GPT-5 really needs a lot of thinking tokens to get there. So again, that kind of goes back to that this is not scaling. And furthermore, many tasks, and I think this paper says 80% of tasks, you don't need a frontier LLM for. So, really save your money, save utility bills on the planet, just use smaller LLMs, call the big LLMs as you need them. But also fundamentally, this opens a new window once again, and there's a new paper that just came out. It's called recursive language models. And remember how I told you how these orchestrators are prompting the big models? Well, what this paper says is, why don't we just do this for everything? So the user gives an instruction. What if we treat instruction as an environment? So let me walk you all through this. So the user gives a prompt to the orchestrator that says, this is what I want done. We're not going to take that prompt literally, we're just going to take it as a high-level guideline. What the LLM will now do is it will recursively break down that task, make sub-LLM calls, and furthermore in this paper what we see is that the LLM crafts this as a problem of a very constrained optimization problem. It's just treating everything you told it as variables. So in this example, what we see is when the user says summarize this book, every recursive call to the sub-LLMs ask for specific chapters. What each sub-LLM does is it'll find the specific chapter, summarizes just that specific chapter, and then they put it back together. Then they kind of make another sub-call and say, can you just verify this, summarize this again? I'm going to take a look here real quick. And one thing that you see is with these, the bigger and bigger depths here, is that these models do better and better and better to the point where like GPT-5 Mini is able to have the same task performance as the big GPT-5, which kind of indicates that to solve a lot of tasks, we're actually just asking bigger models to mentally structure their task. Kind of goes back to the previous talk of these diffusion models internally structuring things. Bigger VLLMs seem to just have that internal structure, but then if we just ask a model to just say, can you just think through this task? Can you break it down into bite-sized pieces? Those smaller LLMs are able to solve it just as well as the big ones if you have enough task decomposition. Kind of goes back to the previous slide. If you have a specialized model for the main bread and butter of the task, that might be all you need. And furthermore, you can also use this as an RL loop. You can see how well this task is going for you, and you have a clear supervision signal, especially today with Hugging Face having the TRL library. RL is easier than it's ever been to do. And the data's abundant now, you can bootstrap your way up. So let me wrap this up for y'all. So context is the bottleneck today, what the context is. Sub-agents are just isolating context, but we need to route things better, which again means what LLM do we want to use for what task? And from there, what we're also seeing is really that when it comes to routing, this is actually a task that appears to be that something is actually very easily trainable. I recommend you just read the Small LLMs of the Future paper from NVIDIA. They also have the Orchestrator paper. They just fine-tuned Gwen 8B for it. And also, if you also look through how big of a data set they used, it was like 10K or something like that, which is way smaller than the data sets these big AI labs are using. So again, most of these smaller LLMs actually have enough data to go do a lot of the tasks you need today. You just need to just break down the task. And that's actually something I've played around with. I've definitely seen that smaller LLMs can actually tackle the really big tasks, and especially if you intermix them with the bigger LLMs in certain areas, they do just as well. And if you make this tractable, I've kind of gone from like $100 to $300 for a task all the way down like $10 to $15 for a task by just not calling the big frontier LLM for every single invocation. So with that, this is my last slide. So that, I'll open up the floor for questions. Yeah, go ahead.
So one thing I found, like if latency is a big constraint, like kind of parallelizing to a bunch of smaller LLM models and then trying to aggregate those outputs like tends to work pretty well. I don't know if the cost saving is quite there because you're replicating that processing, but if you're saving like 10x, you can basically run that. And I found that actually outperforms and is faster than some of the heavy models you might hit with the same problem.
Yeah, that's actually something they bring up in the RLM paper, is that they do actually say that a lot of these tasks are parallelized, like you said, and that's actually something they notice in the task decomposition, that these models are actually able to figure out, how do I parallelize the task as need be? Like in your example, if I'm reading this book, you can read every chapter independently and then put it all together. So very good call out. That's certainly something a lot of these papers also mention now. I would say this is how do you actually get your agents to solve really difficult problems?
Yeah, because I was going to ask, like, also in terms of like the actual performance, like the percentage of like how correct it is, because I've seen a lot of these agents just like go in either in a tangent or they solve it correctly very early on, and maybe someone second guess themselves like halfway through and they throw away a correct answer, but now they just wasted like $30 worth of agentic content.
Yeah, so first of all, for example, this performance orchestrator 8B, just orchestrating a bunch of various tool calls and LLMs together, gets 37.1, where GPT-5, crank up its reasoning, only gets to 35%. And again, GPT-5 is probably a big, large MOE model with trillions of parameters in this day and age, all the way to, I think there's a professor has a talk that it's actually like multiple different models under the hood, and they're just figuring which sub-model per size is actually the best. So based on what you said, it does seem like those routing models do better. And also, like you said, if they just decide to go in circles, just run them locally, let them go to circles on your laptop instead of calling, Claude Opus for, something like, get this $75 for 1 million tokens. So if it goes over 3 times, you don't mind it, Yeah, go ahead.
How well does it work on problems where you can't clearly identify all the sub-problems up front? The chapters is an easy example. It's easy to say, I can take this book and break it up into chapters, but often when you're solving a problem, you break it down into sub-problems, and it turns out that one of your sub-problems has sub-problems. And so how does this deal with that?
Well, it tries to, absolutely, especially the RLM paper, where you're absolutely right that some of the sub-problems will not be apparent until you solve some later problems. This is very true in 3D workspaces. This is very true, for example, in a lot of research tasks. It's not very clear what you need to research next. Or, for example, what I've seen is, if you're doing, for example, like AI video game generation, the fact that you took an action then means that that action can create a problem by itself. That now the next phase is to actually fix. And this goes back to the first part, that these auto GPT models, these deep agents that have planned, that's a fantastic area of a failure point. You've already said I need to task 1, 2, 3, 4, but then you do task 3, you actually need to do task 5, and then you do task 4, you actually need a task 6 to fix it. And the other part of context rot would mean, how often do you see Claude needs to fix something, says I'll come back to it, and just proclaims itself done and never comes back to the task? And then you prompt it again, and it seems to not even remember that it needs to come back to the task, seems to even tell you that this is not an issue, until you have to keep prompting it multiple times and be like, this is the issue, and it's trying to tell you it's really not. Right.
How much do you see, how far do you see this going in terms of specialized models? Right? One of the things being pretty new to code itself and not very compatible, whatever I'm using, whether it's open code and local models or Claude, it tends to hallucinate back and kind of change languages. So I'm wondering if we're going to start to see the reduction of parameters in having these specialized models, like English-only focus.
That's a very interesting research direction, because first of all, this is actually a specialized model. I mean, coding models, they're specialized. There has been a lot of, for example, research into visual action models, and I know we also have a fantastic talk on that. I believe it's more relevant today than it was even a couple months ago, as NVIDIA just dropped a very tiny 8 billion parameter visual action model. So I think that's the thing, the domain is so wide. This is why I think that they're kind of making the point that none of these big research labs can tackle every single problem on the planet. And that's kind of been the claim to fame, is we'll use the biggest model, you solve everything. They're saying, well, hold on, not the case. Not the case. There's certain tasks that are so unique to you and your problem, no one can really solve it. Or the flip side is you're turning on GPT-5 for 100K reasoning tokens, and before you know it, you've just given OpenAI $100 and it's lost context window. You in the back.
Are there any other promising directions for context management?
Well, so there's also this concept of, you can look up Google DeepMind Titan, where the whole idea is that instead of having an LLM that has weights, it kind of has these dynamic weights, which it tries to remember. So the whole idea is like, how do you get an infinite context model? LLMs are also trying to go to an infinite context length. Their claim to fame is they can go 200K to 1 million token context window by just breaking it all up. I think the fundamentals is, how do you rethink tokens in general as the unit of thinking for an LLM right now? And if we get to, for example, there's a paper by Meta called, I want to say it's COCO, Continuous like reasoning, which essentially says that instead of reasoning using tokens, it outputs these special thinking tokens. So it's actually a continuous reasoning space, and you need way less tokens. Because right now we're essentially saying, like, you're just outputting word by word tokens. And that's, I think, the real problem of this. It's actually, we're just trying to work around it still. Okay.
Is there any research into, so for the orchestrator, it's just one, person or agent, but what about like a boardroom of people talking, and, at that level, and then deciding?
So Carpathy just put out a repo called LLM Council. What it actually does is you could just wire up all the frontier LLMs, and there's a counselor that, like, essentially facilitates this chat process. This is such a fast-growing repo. Like, yesterday, someone even added a new UI and all this other bells and whistles on it. There has been a lot of this research, but also this is coming from the fact that everyone's saying, okay, well, now LLMs can actually do reasonable units of work. I'd say, like, early 2023, it was like GPT-4 came out, AutoGPT is cool. No one's really solving anything with AutoGPT in the real world. It's a concept. Today, I would say LLMs actually are solving problems. That's kind of where this research has just emerged. To give you an idea, the orchestrator paper was literally dropped in late November of last year. It's that recent. The LLM paper that I just showed you, this one came out 3 weeks ago. This is like super recent cutting-edge research that is going in this direction because there's so much, and also because there's so many research labs trying to do this. What means that now you have your choice of a model, which means you can pick which model is best for you. And then you can also RL a small model on top of what has been working for you. Again, if you actually look at Claude Code, you look at what it's doing, you can actually look at trajectories Claude is taking, and you can notice that there's areas that it really doesn't perform very well. And that's actually where most of the token usage goes way up, is in areas it doesn't do well. And that's the other thing we see is that with these LLMs, and another thing is, and I did cut it from the slides just due to how dense they are. One thing that they actually have in this paper was that if you asked GPT-5 to be its own router, it preferred itself 70% of the time, meaning that a lot of LLMs think they could solve the problem, and really you're saying, no, go delegate. So that's kind of what you're seeing, that this is a new research direction right now.
What is your intuition about, we're talking about small language models taking care of large tasks, so in this boardroom situation, would SLMs also be good as opposed to frontier models in doing that?
Yeah, that's actually what a lot of the research is saying, that the small models, especially this paper here, this is driven by GPT-5 Mini, where you can get a model that's comparable to it just locally. And it does seem like you can just take a task, and instead of sending it to specialized subagents, just send it to the same type of LLM over and over again. So maybe you're saying, okay, the first time I decompose the problem, let's work on the subtask. You can call your local tiny model multiple times. And I also recommend you look at what Hugging Face has been doing with the small agents, especially small, I can't remember it off the top of my head. They have a model that they showed how they fine-tuned it to work on a GUI, and they only needed 1,000 training examples with RL to get this done. So the other paradigm is RL is unlocking a lot of these environments more than SFT is nowadays. Go ahead.
With the recursive strategy, you're sort of doing a map reduce to spread out the workload of a bunch of tiny little agents. Do you run into the challenge that you'll break the task down to too small of a chunk size, and now you've got 10,000 agents that come back and it's eating up your own context?
I don't think that's what they see in the paper necessarily, but I can see where you're going with this, that it could very well happen in theory. It's kind of hard to just speculate without knowing the task ahead of time. Kind of what I see more so is that kind of the problems I run into a lot is when Claude or GPT-5 takes some action, but then that action actually creates more problems. And then you have to come back and fix a part of the code that they just wrote for one solution that breaks another part of the code base. and it's just like this whack-a-mole with them making errors. That's where they can really come in and say, okay, well, I took in one step. And I think what you're also talking about is, really this, like you said, it's a map reduce, and it's also, if we go take that thing to the next level is, let's think about how Spark versus Hadoop is able to orchestrate tasks, right? Imagine the Spark of LLM design, where now you could say, well, you have these sync points saying, okay, well, let's recombine, or you have split rules and saying, well, you can't split a task more than 5 subtasks at a time now. So I think you're onto something. I think that you could probably figure some cool stuff out and go present here. I think there's definitely a lot of cool stuff there.
So one of the things,
All right.
it's clearly a problem is that context is very critical.
Yeah.
Instead of solving the problem of saying, hey, so we need a smaller model, a bigger model, or we need a reciprocal say we need a bigger model because context is critical. So hopefully they'll think of what you didn't think because it's such bigger context, it's such a smart thing. You put more stuff in it, and maybe the parts of the context that is being a problem will be within that window, and you can figure it out without us even knowing. Where the problem should really be at the cognitive point, say, okay, let's understand the problem and create the right prompt that has all that it needs to have, so it can be a small window that you need. So it's almost like we just need an IDE that would allow us to construct better prompts and also evaluate them easier. Because many times it goes wrong. It goes wrong. What? Within the first second. It's not even finished until
That's right.
But any small model could know it's wrong already.
That's right, and there's actually a paper on this. And that paper is called Weak to Strong Generalization. It came out in 2022, where they actually found that GPT-2 at 100 million parameters was able to steer better than most people GPT-3 at 175 billion parameters. So that's the cognitive load of a model. Meta-prompting is a very easy task, actually. It is not difficult. You just need a lot of examples and training data.
Yeah, but the problem is, part of the thing is like when you say a task, hey, do this thing, and it starts going and it goes modify someplace else. Well, we come to a problem and we know the context. We know, hey, we're not going to change this part. We're going to change this part. So that's where I feel like it's the realness of the context, where we're saying, hey, do this. In some cases, you want it just to do what you told it, but in some cases, you don't want to. But we're humans. It's like, well, why can't you figure it out? Hey, let's make it a big context. No. Yeah, you're a bigger problem. Tell it exactly. Be better at describing, hey, this is what I need.
Yeah, that's actually something the RLM paper went into, where they actually found, and this actually gets back to your point, you reduce too much. They actually found that the opposite can happen, where the model writes a very long prompt to the bigger LLM, or to itself, and then says, like you said, and I think you also alluded to, actually what's happening is they're saying, okay, I want you to solve this problem, and the model says, well, actually, this is 5 sub-problems all in one that you're asking me to do right now. It's not one problem. And so there's one is, can you break it down? The other direction to go into is, can you put a lot of these frontier LLMs, especially in coding environments, into plan mode? But for example, I've seen for Claude to really capture everything, it needs to use 180K tokens. Yeah, go ahead.
I see that you know the literature well, so I'm going to ask you simplest. So the problem we're talking about is, you break this into different problems, right? And then subtasks, and then you say you need, say, n models, right, for this subtask. Now the question is, what about role playing? And then you have the same model. You say, take a role, be an expert in this. You say, be an expert in this again. So you have the same model or fewer models. So now n is more than k. So you have fewer models on the extreme case. Just one model, be an expert in each of those subtasks. Does that make sense? So now there's role playing, not just all the tasks together, but be an expert in each of them, and then come together.
There has been various literature on this. One of them is in 2023, Stanford had an experiment where they had ChatGPT just play every single character in a role-playing game. And what they actually found is that the LLMs were able to actually be very coherent. There's also things like mixture of models. When you hear mixture of experts, there's this idea of like mixture of models, where they also find that routing to different models and having them vote on solutions improves performance significantly. So there is literature on that. Now, I don't know if you're thinking of like dynamic allocation, of saying, does the model know what it's an expert in? I think what we're finding is not really. Models don't inherently know what they're good at unless they can see a lot of training data. And I think that that's been the takeaway from the orchestrator paper, is NVIDIA kind of had to have a lot of data on that task. So that's a very great question. It's a very big area of open research, to the point where I think if you can just try this out, you're gonna have something that's really interesting that, you know, really no one's really thinking about it in that way. I think that's a very interesting question, right? It's like, hey, go role play. You go decide what you want to do. You know, it's almost like voting consensus. I gotta go back to LLM Council. You could just go home tonight, ask Claude Code to just write that in and saying, everyone in the cohort will decide a problem. And then you can also have the counselor, or the chairman as they call them, even decide if an LLM or a certain entity may just be the wrong person to solve the problem.
I have some take against these small language models or the future rating to get that paper.
All right, let's go.
I want to hear your thoughts on it. So, like, for example, like these open costs are getting cheaper for the same performance exponentially. And I think the human resource is probably the biggest bottleneck of these agentic systems. Like, if you want to specialize and find some model, it will take a lot of people to work on and specialize in it. If you look at some of their benchmarks they claimed in the paper, they have a specific tool usage benchmark. And like, I think the first 2-3 words from like Salesforce is like proprietary, like small fine-tuned model that probably took like tens of researchers, and who knows how much time and cost that went into, like, you know, across those researchers. So, like, and I think this paper is slightly biased because NVIDIA published it, so they obviously want everyone to, you know, run their own models with their GPUs. So, I want to hear your thoughts.
Yeah, I think that there's some truth to it that, yeah, right now for small LLMs like these, it is the research bottleneck as humans, though I would say if you wind back the clock, I'd say 4 years ago to like 2022 and further, then you could say the same for the big LLMs too, right? At one point, the big LLMs were bottlenecked by researchers. Now, there's just been so much research that we're not really seeing the big LLMs get better and better as they used to. And we're kind of just seeing that all the big LLMs have kind of converged to the same area now, where, you know, it's literally now they're all identical. I think that to some extent, yeah, training your own model, I know they make this promise. You're not wrong in saying that's not simple, and you're right. On the other hand, though, Hugging Face has a paper they published about a month ago, maybe 2, where what they do is they actually give Claude skills and tools to go train open source LLMs, and they actually find that Claude can craft data sets for those LLMs and like distill into those models. So that's the other thing, is that we have these big models, we can distill them into small models. Again, I mean, benchmarking, you know, in certain areas, yeah, you can benchmark some of these models. In some regard, there is a generalization gap between the big and the small. That's very true indeed. But though it's saying that in certain subtasks, that doesn't exist. For example, in computer vision tasks, there's not much of a difference between the big and the small LLMs. If you look at certain things like, you know, task orchestration tasks, or, you know, go find me the right file, a lot of these smaller LLMs are just as, you know, good as the big ones, you know. And I also think a mixture of experts has really pushed that frontier. You gotta look at what does Quen 3, the 30 billion MOE do, even though it's just 30 billion parameters activated. it starts approaching the performance of the really big ones. So yeah, I agree to some extent that yes, some amount of benchmarking, some amount of difficulty in actually training these models, that's actually true. But I do think the tooling will get better and better and better though. I think that some of these bigger entities like Hugging Face are definitely trying to solve that problem. Yeah, go ahead.